You are staring at a monument to a broken law of physics. That bump on the back of your phone is not a design choice, and it is not a marketing trick. It is a physical confession, proof that engineers lost a fight against a lens barrel that needed 10 times more room than a slim phone can give. In the next few minutes, you will learn which law broke, and why the fix forced your phone to grow not one eye, but an entire team of them. A professional photographer carries one camera body and swaps lenses. A wide lens for a landscape, a telephoto for a distant subject. Your phone cannot swap its eye. It must carry several eyes, each one permanently fixed, to see the world in different ways. Here is where the lie begins. The box lists a 26mm wide lens and a 52mm telephoto. Numbers borrowed from professional full-frame cameras, so your brain has something familiar to compare against. The physical truth inside your case is far stranger. That so-called wide lens sits barely 4mm from its sensor, a speck of molded plastic focusing light onto a chip roughly the size of a baby aspirin. On a professional single-lens reflex camera, that same distance stretches past 40mm, 10 times the room to work with. A true zoom lens needs physical depth. Glass elements slide back and forth inside a barrel, changing the focal length as they travel. Your phone is thinner than a deck of cards, and that barrel would need to stretch several inches to do the same job. There is no room inside for glass to move. A single lens cannot optically zoom on a smartphone, not because the engineers lacked skill, but because the geometry does not exist inside the case. The phone has no choice left but to cheat. The cheat is a team of specialists. Your phone does not contain one camera. It contains 3 or 4 completely independent camera systems, each with its own lens and its own sensor, sitting side by side, millimeters apart, each locked to a different focal length. When you pinch to zoom from 1 magnification to 3, nothing physically moves inside the phone. The device simply hands the job from the wide-angle specialist to the telephoto specialist, switching cameras faster than you can notice the seam. It is the engineering equivalent of a photographer carrying 3 separate cameras on one shoulder, each locked to a single lens. But could one exceptional lens replace this whole crowded lineup? For years, one company tried to prove exactly that. The Google Pixel shipped for years with a single rear lens, and it still produced stunning portraits with soft, blurred backgrounds. It shot detailed images in near darkness through pure software processing. It did all of this without a telephoto lens, without a depth sensor, and without an ultra-wide camera. Its portrait mode was a kind of magic trick. Software identified a human face, then digitally blurred the pixels around it, guessing at depth rather than measuring it. The result looked stunning, but it stayed fragile around complicated edges like loose hair or a glass of water. A phone with 2 offset lenses does not guess. 2 cameras capture the same scene from slightly different angles, and the processor compares the shift between them to calculate a true depth map for every pixel in the frame. That is a 3-dimensional measurement of the world, not a filter layered on top of a photograph. The Pixel proved software could fake depth brilliantly. It also proved that faking it has a ceiling, and that ceiling is built from something even smaller than the lens. A smartphone sensor is roughly the size of a baby aspirin. A professional full-frame sensor is roughly the size of a postage stamp, more than 20 times the surface area. A bigger sensor catches more photons, and more photons mean less noise, wider dynamic range, and truer color. A single smartphone lens is starving for light, no matter how clever its software gets, like trying to fill a swimming pool through a garden hose. The fix was never going to be one perfect sensor. The fix had to be a team of sensors, each specialized, working in parallel. The main wide camera carries the largest sensor and the widest aperture, built to gather as much light as possible for everyday shots. The ultra-wide lens trades away some of that light for a sweeping field of view past 112 degrees. The telephoto lens accepts a narrower slice of the world in exchange for magnification. What happens once every specialist has captured its own separate image? Someone still has to stitch them into one photograph, in a fraction of a second, before you even lower your hand. A team of specialist lenses is useless without a conductor. The instant you press the shutter, the phone fires the wide lens, the telephoto, and the ultra-wide all at once, capturing a burst of raw data from every sensor simultaneously. A dedicated image processor built solely for this task goes to work immediately. It compares the parallax shift between the offset lenses to build a depth map, merges sharp detail from the main sensor with color data from the wide lens, and adjusts exposure a dozen times in milliseconds. The photograph that lands in your gallery is not a single exposure. It is a computational construct, woven together from 3 separate cameras working as one, capable of a backlit portrait that a bulky professional camera body would genuinely struggle with. But here is the problem the team still had not solved. A standard color sensor sits behind a microscopic grid of red, green, and blue filters, and that grid blocks roughly 2/3 of the incoming light before it ever reaches the pixels. Phones like those from OnePlus added a monochrome sensor that strips this filter away entirely, seeing the world in pure brightness and capturing more than double the light of a color sensor. The processor merges the two, pulling texture and clarity from the monochrome eye and hue from the color eye. That solved detail. It never solved distance, because a true zoom lens still could not fit inside a case only millimeters thick. The Periscope lens cheats that limit entirely. Light enters through an opening on the back of the phone, strikes a prism angled at exactly 90 degrees, and travels sideways along the length of the case instead of straight back toward it. The lens barrel, with all its zooming glass elements, is not sitting behind the camera bump. It is lying on its side, hidden inside the chassis, and the width of the phone becomes the depth of the lens. This is folded optics, and it is how a case only millimeters thick reaches a true 5 times or even 10 times optical zoom. That bump on the back of your phone was never a design failure or a marketing gimmick. It is the visible proof that a team of engineers solved an equation with no clean answer, giving a professional photographer's versatility to a device thinner than a pencil. You cannot bend the laws of optical physics, so you build a team instead. 3 or 4 specialist cameras bolted together side by side, guided by a silicon brain that fuses their separate visions into one frame before you even blink. The next time you feel that bump under your thumb, you are not touching a flaw. You are touching a pocket-sized team of optical specialists that beat physics to capture your world.